So question 7, we have a student investigating acceleration using gliders and air track and light gates. So the air track reduces friction between the glider and the track to 0. So you have an air blower that pushes air through this tube and it enters the air track, and there are tiny little holes along the length of this air track that lift up this glider, and then that means the glider can move anywhere it wants to along this air track, and the forces of friction are going to be minimised, so there won't be very much friction at all. You've also got light gates, which tell you how you can use a computer alongside the light gates to say how fast it's travelling at this point and this point. And then if we go down, we have a string attached to the glider which pulls it forwards, that goes over a pulley, and you have an accelerating force provided by the masses and holders, the slotted masses over here. So the glider was released from rest and moved along the track. The mass holder hit the ground, so this doesn't sound good. It hit the ground before the car passed through the second light gate. So if the mass hit the ground, then it's no longer going to be exerting a force on the glider. So we're looking for something like that. So the resultant force on it would decrease to 0. Now, if we have no resultant force, that means there's no acceleration. So the acceleration would decrease to 0 as well. Certainly wouldn't increase, so it can't be that one. Again, this wouldn't happen, and because the acceleration is 0, it wouldn't increase in speed either. So yeah, happy with these two. Next, the mass holder should not hit the ground before the car passes through the second light gate. One thing we could do, well, one option would be to use a shorter string. That would be the most obvious one. Another option, if we have a look, we could move this light gate closer to the other one. That means it would still be falling as it passed through. Move right hand light gate. To the left. And I guess you could use a taller table as well, but the most sensible thing would be use a shorter string. Okay, we have the student increase the resultant force acting on the glider by adding more masses to the mass holder. She calculated the acceleration of the glider for each resultant force, and here we have a table of results, and it's telling us that the student made 2 mistakes. Now the first one's jumping out at me straight away. If you can look at all these numbers, they're all given to 1 decimal place, and that kind of matches the acceleration readings in the table as well. So this is so let's move that up. Mean acceleration for 0.20 newtons given to the wrong number of decimal places. What they should have done is round that to 1 decimal place. So if we round that to 1 decimal place, we get 1.3 meters per second squared. The next mistake is a little bit harder to spot, I think. So I had a good look through here, and I had to use my calculator to find this. But if we look at these 2 values, these are very close. This one, however, is way out of line, so I think this one is an anomaly, but they've calculated this mean without discarding the anomaly. So mistake, the acceleration mean for 0.98 newtons calculated with the anomaly, which is not what we want to be doing. So the correction should be, well, we're going to discard that anomaly. We're going to do the mean of 6.4 plus 6.4, which is 12.8. We're going to divide that by 2 rather than 3, which gives us 6.4 meters per second squared. So the correction should be 6.4 meters per second squared. Right, a conclusion for this investigation. So let's see what happens. if we look at, let's take a look at two resultant forces. So we'll look at 0.20. 0.39 is almost double that, and the mean acceleration is also almost doubled. This is increased by a factor of 3, and that's almost increased by a factor of 3 as well. So that suggests to me that the acceleration is directly proportional to resultant force. So essentially, if you were to plot a graph of your findings, you would have a straight line through the origin with a positive gradient. 7.6, different experiment. This time they're keeping the accelerating force, the resultant force, constant, and they're changing the mass of the glider. So that should probably decrease the acceleration, but let's see. We have a table of results here, and it's asking us to plot a graph below. So our first reading was a 0.06. That takes us up to 3.5. Use a cross when you're plotting this, please, not a dot. You'll notice I'm using pen as well, because that shows that better in the video. Normally you should be using a sharp pencil. Our next reading was 0.08, and that took us up to 2.6. So each single square represents 0.1, so that's 2.5, and one square above 2.6. 0.10 goes up to 2. Nice easy points to plot here. 0.12 takes us up to 1.7. 0.14 takes us to 1.4. And there, like that. And it says draw a line of best fit. Now, again, maths, a line of best fit will always be straight. In science, it can be curved. So I'm going to move my paper around there like that, and I will use a pencil this time, and we'll kind of practice drawing the curve several times before you even put pen to paper. Then that's fine. Bit of a wiggle at the top here, but nothing to worry about. So as long as you have your curve as close to as many points as possible, and it's a relatively smooth curve, that should be fine. And finally, describe the relationship between mass and acceleration. So this shape of graph, kind of a decreasing curve, we say is inversely proportional. So all we have to do here is say that acceleration is inversely proportional to mass. Really, all we have to write is inversely proportional. That would get us the mark, but to make a full sentence, I've done that.